When looking at the uses of radiation, we regularly need to look at the properties of the three different types, but we also need to know about the half-life of a particular type or isotope that gives out that radiation as well. Before we can discuss half-life, we need a good idea of what I mean by radioactivity, and I mean specifically the activity part of that. Activity is a measure of how many nuclear decays happen in a given time, and the standard unit for that is the becquerel, where 1 becquerel is 1 nuclear decay per second. Okay, 1 nuclear decay per second. So, right, we know that activity is the number of decays per second, but what is decay, and how do I describe it, and how do I describe its qualities? Well, the first quality that is most important about it is it's random. The word random should bring in connotations of things like dice rolling or maybe even flipping a coin, but it has a very specific meaning that you need to be able to recount in an exam if you're asked about what does this mean. And the fundamentals are it cannot be predicted. You cannot predict when a specific atom itself will decay. Another important detail is that if an atom is unstable, its nucleus will decay at some point, but you cannot do anything to change the likelihood of that happening. So if I've got, say, carbon-14 from my earlier examples about beta decay, I cannot predict when that carbon-14 atom is going to undergo beta decay. I can't say if it's going to be tomorrow, I can't say if it's going to be next week, I can't say if it's going to be in 10, 15, 100 years time. I just know it's unstable and therefore it has a chance of decaying. The more unstable the nuclei is, the more likely it is to decay in a given time than another one. So some materials have got a very, very high chance of decaying because the configuration of protons and neutrons inside the nucleus really don't want to stay that way. They'll rather undergo a nuclear decay of some form in order to become more stable. Again, the emphasis here is this: whilst we can say it will decay, we cannot predict specifically when. A random decay means you cannot predict when it's going to happen. Nuclear decay being random can be problematic, and on the surface of it is an incredibly problematic issue. The only thing that works in our favor is that there is a probability that an atom will decay within a given time. That probability is a key thing, and it means that we can use statistics and large numbers of atoms as exist within any given sample. You've got to remember from your chemistry that a kilogram of material includes a vast number of particles. Even a gram of a certain materials contains ridiculously large numbers of particles, statistically valid and important numbers of particles. Now, the example I'm going to use in this little simulation includes 200 particles. So not really anywhere near the kind of scale of things we're talking about when we're talking about atoms within a few grams of a material. However, each of those atoms will have the equal chance of decaying in a given time, and I'm going to take samples of this every 5 seconds whilst we're running this little simulation. In the first 5 seconds or so, half of them have gone. Okay, so in the next 5 seconds, what do I expect? 100 more? No, 50 of them go. Then if I go for another 5 seconds, 25 of them have gone. Now, this sample of 200 gives me a pattern that I can look at, interpret, and potentially from that find something useful. And if I was to repeat this over and over again, because it is random, I will see some variation in this pattern. There may be, say, starting with 200, I go down to 95 or 120, and then in the next time down it could be 40 rather than 50. The random nature of it means it's never going to be 100% reliably that 200, 150, 25. There's always going to be some variance in and around that, but it will follow that pattern. And that pattern that when it's analysed appropriately gives us the half-life for a given radioactive isotope. There are two definitions for half-life that you need to know. You need to know that half-life is either the time it takes for half of a radioactive sample to decay. So if I had 20 kilograms, it's the time it takes for that 20 kilograms to drop to being 10 kilograms worth of radioactive material. Or it's the time it takes for the activity of the sample to halve. So if I had a radiation detector next to my radioactive sample, it's the time it would take for it to go from 500 becquerels to 250 becquerels. Okay, but those two times are the same because the activity is dependent on the number of particles that exist within the sample. So if the number of particles halves, the activity is going to halve. Okay, but half-life itself is defined as the time it takes for the half of the radioactive sample to decay, or the time it takes for the activity of a sample to halve. You can be asked to find this from a graph in an exam. So on the right hand side, I've produced a graph of unstable atoms left in a sample versus time, and it's based on the simulation that I've shown you already. There's a simple procedure that if you follow it, you will not get this wrong. But you must remember to do a couple of the key facts in this, because invariably it will say something like show on the graph how you've obtained this number, and you must demonstrate you're working out for this. Otherwise you can lose 1 or 2 easy marks. Even though you get the right answer, you won't get your marks for your working out. Okay, first thing you do is you look at the initial value on the y-axis. So for this example, as per the simulation, it's 200. You then halve it, you get 100. After that, you draw a horizontal line across to where the curve is, and you stop at the curve. You then draw a vertical line down from that point to the x-axis, and that gives you the half-life. So in this case, it's 5 seconds. Okay. Now, if you have time, or if you want to, you can potentially check this. If you halve it again, the gap should be 5 again, and halve it again, the gap should be 5. Effectively, every time you're halving it, you're getting the same time interval along the horizontal axis. That is how you determine the half-life using the graph. It's a method and procedure that you really need to be able to communicate accurately and show that you've done it. So draw those lines on those graphs. You're expected to do it, make sure you have. Why is it important? I mentioned that when we're considering radioactive sources and their uses, we need to think about the properties of the radiation and its half-life. Well, a couple of the applications that we've discussed so far. We've discussed smoke detectors, and we've discussed medical tracers, and we've discussed thickness control. A short half-life source in a smoke detector or a thickness control machine would mean that it would need replacing more often, so ones with much longer half-lives are used. We don't want to have to replace our smoke detectors every 2 years or every year. So what we do is we use americium-241, which has got a long half-life, a few decades if I remember correctly, and that means that the smoke detectors that you buy will be good and continue to operate until much longer life, probably outliving the odd time that you'll stay in that house. The clue that the half-life has got to the point, or the activity has got below an acceptable level, is the smoke alarm will just keep on sounding because there will be no current flow. On the flip side, you don't want to be using long half-life medical tracers. You don't want to be increasing the exposure to nuclear radiation to a patient who you're trying to diagnose or check on, like if something's working. So short half-lives are used. Typically, in the case of medical tracers like technetium-99, that's about 6 hours. So after a day, you've got a tiny fraction of the original radiation that you had that was being used to diagnose or identify where the blood is flowing through the body. Key points from this video about half-life. Activity is measured in becquerels, where 1 becquerel is 1 decay per second. Half-life has got two definitions, and you should be aware of both and be able to repeat both. The time it takes for half of a radioactive sample to decay, or the time it takes for the activity of a sample to halve. In order to find the half-life from an activity or number of atoms left graph, you need to take the initial value from the y-axis for when time is equal to 0, halve it, draw a horizontal line across to the curve on the graph, and then draw a vertical line down to the time axis, and the time reading you've got there will be the half-life value.